everyone, welcome back to another session of the chapter Carbon and its Compounds. In the previous sessions, we have already understood some basic properties of the carbon, its atomic number, its electronic configuration, why carbon forms covalent bonds, what are covalent bonds and what are the types of the covalent bonds. In today's session, we will move ahead in the chapter and will start another new topic, that is allotropes of the carbon. So let us begin the session. First of all, we will try to understand that what do we mean by the term allotropy and what are allotropes of the carbon. Now, whenever an element exists in more than one form which are having different physical properties but similar chemical properties, then all those forms are called as allotropic forms or allotropes, and this property is called as allotropy. Now, first of all, understand that what are physical properties. Physical properties are the properties which you can describe or tell by seeing from your eyes, that is from your naked eyes you can say, like about the size or color. All these things you can observe. But when we speak about chemical properties are basically about the chemical reactions. Okay. So, here whenever an element occurs in more than two forms which are having different physical properties but identical chemical properties, then all those forms are called as allotropic forms or allotropes, and this property is called as allotropy. Now, here the element is carbon. Okay. So, carbon is the element and carbon occurs in various forms. The most common example is coal also here. Okay. Coal, diamond, graphite and fullerenes. Okay. Now, you all have seen diamond. Diamond is the hardest known material. You know that it is very hard. Another property, it shines. Okay. But if you see graphite is black or grayish in color. It is soft and little bit slippery also. Fullerenes you have not seen, so I will not discuss it, and you all know that coal is again black and it is very brittle in nature, right? So you are seeing that they all are forms of carbon. Coal, diamond, graphite, fullerenes, they all are forms of carbon, right? But physically they are showing so much differences, right? So whenever an element is in two or more forms having different physical properties but identical chemical properties. Now, identical how? For example, if you burn coal, you will get carbon dioxide. If you will burn diamond, you will get carbon dioxide. If you will burn graphite, you will get carbon dioxide. So, chemical wise, they are same. So, in this way, what we can say, carbon occurs in more than two forms which are physically very much different from each other, but chemically they all are same. So, they all are called as allotropic forms of carbon, and this property of carbon is called as allotropy. Okay, now let us start with the diamond. There is a brief description of the diamond in your book, so I will also start with that. Now, if you see the structure of the diamond is having a tetrahedral arrangement, that is each carbon atom. So, suppose this is the carbon atom, okay, in the center. Now, this carbon atom will have tetravalency, you know, okay, tetravalency, every carbon is tetravalent. That is, it has got a valency 4. Right. So, every carbon atom needs to satisfy its 4 valencies. So, here this is carbon atom in the center. It is forming a single bond with the neighboring carbon atom here. It is also forming single bond with the another carbon atom here, third bond with this neighboring carbon atom, fourth bond with this carbon atom. So each carbon atom is attached to 4 other carbon atoms by strong single covalent bond. Okay, we have already understood single covalent bond, that is when there is a sharing of single pair of electrons. So carbon is usually having 4 sides or 4 valencies satisfied. Here in the diamond it is like this. Every side is occupied with the neighboring carbon atom, which gives it a very rigid hard structure. The 4 surrounding carbon atom lies at the 4 vertices of a regular tetrahedron. If you see here, this is a tetrahedral structure. Okay, and the neighboring carbon atoms are lying at the vertices of a regular tetrahedron with a carbon in the center. Okay, and this gives it a rigid 3-dimensional network, and this makes it the hardest known material. Hardest known material. And because of the strong bonding, because of the strong covalent bonds, there are no free atoms or the ions, and that is why diamond is a poor conductor of heat and electricity. Now let us start with the next allotrope of the carbon, which is graphite. Okay, now this is graphite. Graphite, you all know that it is a grayish black substance. You all must have seen it in the pencil lead. It is used. Okay, it is used there. So it is a grayish black substance. It has got a very little shine to it, and it is quite slippery also. Now if you see the structure of the graphite, the carbon atoms are arranged in a hexagonal ring. This is a hexagon, see this one. This is a hexagonal ring. So carbon atoms are arranged in a hexagonal array of rings. Okay, and they are arranged in sheet, like this is first layer, you can say from this diagram, and this is second layer or another layer. So each carbon atom in graphite is bonded to 3 other carbon atoms in the same plane, forming hexagonal rings. The structure of the graphite is layered. Graphite structure is in layers. Okay, so in each layer the carbon atoms are arranged in a proper hexagonal rings, and each of the carbon atom is bonded with the 3 neighboring carbon atoms. Like for example, let us see this one. Okay, this one you can see, this is a carbon atom. It is attached with this carbon atom, it is attached with this carbon atom, and this is attached with this carbon atom also. And its 4th valency is satisfied with the another carbon atom in the another layer. Okay, so in this way the 4 valencies of the carbon are satisfied here, but the arrangement or the bonding crosses from one layer to the other layer. Okay, and these bonds which are going from one layer to the another layer are called as van der Waals forces, and these forces are very much weak. They are weak. Okay, so first of all, this layer arrangement of the carbon atoms make it a 2-dimensional structure, and second point is that they are having weak van der Waals forces between the layers. Because of the weak van der Waals forces, they or you can say the structure of the graphite is slippery. That is, the layers can slip past over each others. Layers can slip past over each other. And because of this, graphite is used as a lubricant. Okay, and graphite is also a good conductor of heat and electricity. Why? Because the weak van der Waals forces allows the movement of the atoms or the ions, and thus it makes it a good conductor of heat and electricity. Now let us go to the next allotropic form of the carbon, okay, which are fullerenes. Fullerenes are actually the recently developed form, recently identified allotropic form of the carbon. They are in the form of a sphere. So they are spherical in shape, containing even number of the carbon atoms ranging from 60 to 350. The most common example of fullerene is C60. C60 fullerene. Why? Because it is more stable and it is the first to be identified. 60 is showing the number of the carbon atoms arranged in it, and the carbon atoms are arranged in the form of a soccer ball or a football, okay, and it is also popularly called as buckyball structure. It contains 26 membered rings and 12 5-membered rings. That is the 6-membered ring, that is hexagons are 20 and there are 12 pentagons, 12 membered rings in it, okay. It has got its name from the Buckminster Fullerene. Buckminster Fullerene is the name of the person who has designed some domes in US, okay. They are also called as geodesic domes, okay, and the structure of these domes was found to be very close to the fullerenes. So that is why the name fullerenes was given, or at some places they are also called as the Buckminster fullerenes. Okay, so with this we have finished the allotropes of the carbon. Now we will try to understand that what makes carbon the versatile element, or why carbon forms the largest number of the compound. So we are trying to understand now versatile nature of the carbon. First reason behind the versatile nature of the carbon is catenation. Okay, catenation is what? Catenation is the self-linking ability. Like for example here, this is a unique property, here I forgot to add T. This is a unique property of self-linking of carbon atoms through covalent bonds. Now if you see the example here, this is a carbon atom, 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 and each carbon atom is linked with each other by covalent bond, So you can see here, catenation is what? It is a self-linking ability of the carbon. That is, it can link with the neighboring carbon atoms by covalent bond. It can be a single bond, it can be a double bond, it can be a triple bond also. Now, because of this self-linking, it is not only forming the straight chain compound, it is also forming the branch chain, it is also forming closed chain or a ring kind of structure also. Okay, so the same thing is written here, that this is a unique property of self-linking of carbon atoms through covalent bonds to form long, straight or varied chains of the varying length or rings of the different size in catenation. This is one carbon atom attached to the next carbon atom, attached to the next carbon atom, attached to the next carbon atom. So here you are seeing that carbon atom is linking itself to the neighboring carbon atoms by covalent bond. Okay, so this is catenation. So this is one property which is the reason behind the versatile nature of the carbon, or you can also say that because of this property, carbon forms the largest known compound. Now, the second property, which is tetracovalency, that is, you all know that carbon valency is 4. 2, 4 its electronic configuration. So it is halfway filled. It is the second shell. Maximum it needs 8 electron. Out of 8 it is already having 4. So it is in need of 4 more. 4 more, and that is why its valency is 4. So carbon shows us tetravalency. That is why carbon can form many bonds or many structures or many compounds. So this is another property of the carbon which is responsible for the versatile nature of carbon. Now third is tendency to form multiple bonds. Like for example, carbon forms single bond with the other carbon atom, carbon can form double bond also, carbon can form triple bond also. Not only this, it can have multiple bonds in the same compound, okay, like this. no, this one is not possible here. Okay, like this. So you are seeing that carbon can form multiple bonds in a compound. Okay, so this is another reason that why we are seeing that carbon forms so many number of compounds. So due to the small size, carbon form multiple bonds, that is double or triple bonds with other carbon atoms, with the oxygen, nitrogen, chlorine, and with the hydrogen. Okay, so now let us go to the next property which is making it again versatile, is isomerism. Now at this stage isomerism is little difficult to understand. Why? Because you have not understood that how to write the alkanes or the hydrocarbon and its naming, but still I'll give you a brief here and I'll show you the isomers in next session. If a given molecular formula represent two or more structures having different properties, the phenomenon is called as isomerism, and the different structures are called as isomers. Okay, so the formula is same but the structures are different, then this property is called as isomerism and the structures are called as isomers. Once we were when I will explain you the hydrocarbons, okay, which will be our next topic, there I will show you the hydrocarbons and there I can show you that they are having the same formula but different structures. Okay, so there you can understand it in with one or two example, but right now it is quite difficult for you to understand. Okay, so let us meet in the next session. I am ending this session here. If you are liking, then please subscribe to my channel and hope to see you soon. Bye bye.